Okay.
Absolutely, no issues.
Thanks. Okay, so we're going to start for today's session.
Sure.
First of all, good evening, everyone. On behalf of IIT Kanpur, I, Arindam Mitra, want to warmly welcome all of you for today's fourth session of PERA 21. The topic of today's industrial session is on Siemens Smart Infrastructure. For delivering today's session, we are fortunate to have with us the two distinguished personalities from Siemens, Mr. Sebastian Kuhn and Mr. Narayan Menon. Mr. Kuhn is heading a portfolio management team for grid edge solutions within Siemens Smart Infrastructure. He is developing energy management solutions that can be applied globally within the field of photovoltaics, battery storage, and electrical vehicle charging. As a graduate engineer in electrical engineering, Mr. Kuhn has held various projects lead positions since 2009 for electrical systems of power plants and for stationary battery storage systems at Siemens. Since 2017, Mr. Kuhn is responsible for the design of technical solutions in the field of distributed energy systems and drives the development of portfolio packages for the energy infrastructure. Our second speaker is Mr. Narayan Menon. He is the regional technical lead of Middle East and Asia Pacific for energy performance services within Siemens Smart Infrastructure. Mr. Menon develops and executes facility improvement measures both for supply and demand side of various facilities. In addition to this, he is supporting strategic project development activities for countries within the APAC and MENA region. Prior to joining Siemens, he was a design technical lead for a major Indian MNC and was responsible for the overall design and execution of MEP HVAC projects for large commercial buildings and airport. So with this, I would like to hand over the screen to Mr. Khan and Mr. Menon and request them to deliver today's session. Thank you.
Thanks a lot. Okay, so can I share my screen, Arindam?
Sure.
I hope it's visible.
Yeah, it's visible.
Great. So good evening, one and all, and really appreciate you inviting us for this program, and we have been looking forward to it for the past few days. Now, Siemens Infrastructure, Siemens Smart Infrastructure is a division which basically looks into facility improvement measures, both on supply and demand side. So when we talk about supply side, it's all about distributed energy systems, but we also have a team working on the demand side, which is to do with optimization of chillers and the thermal part of a building. So we have been extensively, our group has been in the field of energy for the last 12 to 15 years. And right now we see a rapid trend growth towards energy optimization. We have been associated with IIT Kanpur, and we have been a partner with them to develop the microgrid project, which is currently in the commissioning phase, and hopefully we execute it in the next 1 month and hand over it. So we are privileged, in fact, to be associated with IIT Kanpur over the past 2 years. And so thank you one and all for joining. And now the first part of it would be taken by my colleague Sebastian, and then I would then pitch in some more ideas and some analysis. So Sebastian, please go ahead.
So thank you. So yeah, today we would like to take you on a journey, let's say with digital tools and software, how to exploit full potentials of PV and battery next to buildings, and also then in the context of microgrids. And yeah, when we just have a look in solar and battery, maybe Narayan, we can have a look on the next slide and to see why should we install battery in solar. So what are the drivers to install them? And so main driver, that's all relevant now for India, is the reduction of CO2 emissions that comes with the reduction of fossil fuel energy. And in this context already next to the building, it's also related to green energy generation on site. So not just, let's say, purchasing green energy from the grid, it also means really generating green energy within microgrids on site. And yeah, also an important point is increasing of resiliency, which you can reach when we install battery systems within a microgrid next to the buildings that will be supplied. Yeah, especially when we look then at critical infrastructures, this is a very important topic. And also if you have a grid that's quite weak and where you're facing a lot of grid outages. Another context where the installation of battery in PV makes sense is if you want to increase your flexibility in the energy consumption and demand, and also in the generation. And there are upcoming models where you can commercialize your flexibility with your own microgrid at markets like the demand response markets that are coming up in more and more countries. Another point is also that you can avoid the extension of your grid connection capacity, especially in the context of more and more EV charging, electric vehicle charging stations coming up that need to be installed next to an existing energy infrastructure that was not designed for such power ratings. Systems like a battery are very useful when you look at fast charging applications where you have to deliver high power in a short period of time, and that might not be covered by the existing grid connection capacity. Another important point is also, of course, reduction of energy demand costs. So this can be peak shaving applications where you say, okay, I need to get down my power peaks because that will be built by the utility. And also I want to increase my self-sufficiency with my system on site. And also, if you have a look on just building standards, which are going more and more into the direction of sustainability for buildings, there are more standards and certificates that give points really to green on-site generation, as well as to flexibility or demand response capabilities. And that's also becoming interesting in the context of equity funds or general, let's say, financing, because those financing funds are looking more and more into sustainable investments. And therefore, also buildings need repair of that they are certified as a sustainable building. And therewith, PV and battery storage can help. And Ariane can go to the next slide, so we can have a look on where this might make sense to install PV and battery storage. So I'm starting here on the top left. So especially with industrial buildings, it might be the case that there are industrial consumers inside that generate high peaks. So a battery might help to shift those peaks or to capture them. And also in the production, it's becoming more important that the production of products is made sustainable. If you just maybe have a look at battery manufacturing facilities, for example, but also it's important that the energy used for producing the product is coming out of green sources and not fossil fuels. So really also related to the decarbonization. And when we have a look at campus, we're looking at very complex infrastructure. And there with PV and battery can also help within this complex infrastructure with this microgrid to balance energy inside of this microgrid. When we have a look at office buildings, so especially here coming up in Europe and US Americas, more and more employees working in these office buildings that want to come by their car still, but maybe they're going to change now to electric cars. And they also want to have the capability to charge their electric cars there on site, in the best case, then with green energy. And therefore also these employers need to take care of that they can satisfy the needs of their employees. When we have a look at commercial buildings, for example, at retailers, it's all the same case. EV charging also has impacts there. If, for example, a customer there wants to park there and during his shopping tour, he wants to charge his car on a fast charging application, we also would like to install a higher capacity of the grid connection, or maybe you can choose a battery system that can supply this high power for a short period of time to this fast charging application. And also these commercial enterprise companies want to reach their sustainability goals they have set up. And as we look at infrastructures like hospitals or airports, I think the most important point is that this operation can run continuously without any interruption, even if there's a grid outage. And therefore, battery storage system can help to cover those or bridge those grid outages. In the area of residential applications, it's coming up more also in Europe and US, that also at home, as the people want to use green energy by installing PV, but also might use then an EV car and they want to charge their car with green energy, but maybe during the day they're on work, so they can't charge it directly from PV into their car. So a battery system in combination also makes sense there. So we also have a small microgrid at home. And we can go to the next slide. So I want to show you how we can exploit these potential for each customer project. That's very individual. So on the first point, it's really related to get a clear picture out of what's the baseline of a project or of an energy infrastructures installed. You're starting with the data acquisition. This can be made with interviews or checklists, and also with getting historical data, maybe from the utility meter, or if there is available already, a billing automation system. So billing automation systems, they also can help to generate transparency of the consumption. And if there's might be not such detailed information available, it could be useful within a study to install a temporary monitoring measure equipment at the points of interest in your substations, where you say, okay, I'm looking at the substation because we tend that there are those consumers that generate peaks or maybe those really high energy demanding consumers installed there. So with this temporary monitoring, you also get much more transparency about your load profiles and what could be then optimized therein. Another point then after this, if you have, let's say, made first data acquisition, you need to analyze the data. And first of all, you need to set up once the baseline with the data you have, and you want to discuss them with the customer. What's the target? Where you want to go for? Are you going for decarbonization? So do you want to be carbon neutral, let's say, within X years? Or it's more related to, savings on energy you want to reach. And then with this demand profile, you can analyze whether there are peaks that can be mitigated. You can analyze the tariff structure, whether it makes sense with the battery storage, make any time shifting from high tariff periods to low tariff periods. And also if there might be some subsidies that can be taken on or tax benefits you can benefit from. Furthermore, of course, if you're looking at PV, it's need to be clear, okay, what can I install there? What is the place available area for PV installations or for other equipments that might be useful? And last but not least, it's very important that you know the user behavior, especially when it comes to EV charging or other things, because if you want to install an energy solution, a new microgrid on site, that should enable and satisfy the customer needs and not limit them. And therefore, you need to be aware of the user behavior, and so that you really take care of it and there's no loss in comfort for the user. And when it comes then to the system simulation, first of all, you need to define a scenario space. So what time period you're looking at if you want to go for a simulation of such a microgrid you're looking for. And also about the search space with the components I've mentioned before. Yes, and then you can import these demand profiles and generation profiles with other software simulation tools. And then you also need to define which kind of optimization I want to go for. And there are different dispatch algorithms that we have been set up within Siemens that have different advantages and disadvantages and go for different targets. And then on the next slide, I want to show you how we can show this simulation process step by step and how this is set up. So as you've seen before, within an infrastructure, energy infrastructure next to buildings or microgrids, they can be quite complex. So there's not just, let's say, the electrical part of it you need to take care of. There might be also some systems that are interlinked, let's say, to the microgrid, like heat generation, cooling generation, and other systems. And in order that you can really simulate the entire system with thermal bus and with the electric bus, we have set up simulation software that can do so. And thereof, you need to, of course, feed it first with the right input data. And therefore, we've said, okay, it's best if you have the baseline with the demand profile from the existing energy infrastructure. And as we said, it can be made with data acquisition, or you can also, if you don't have precise data, you can also make your own demand profile within this tool by your own. Especially when it comes to EV charging infrastructure, for example, we also can include there a generator for EV charging demand profiles for the charging process. Another important point is really when you want to go for this economical optimization, that you have a clear picture of the tariff infrastructure, and that needs to set up in the simulation as well. So what's the tariff for the import from grid, and with these tariff periods, what do you get for maybe export from for energy into the grid? And what do you get maybe from then consumers there that charge their EV car? So, and also regarding what's important to have a look on those price adjustments within the simulation over the years and price escalation rates, because when you set up a project, it should be then really economic over the entire project period, and therefore need to take care of what parameters might change over the project lifetime. And then with the optimization configuration, we have already developed a small optimization algorithm that can be parameterized by, let's say, the type of components that can be installed. And also then you can set KPI targets you want to go for, example, for decarbonization. And then this optimization, pre-optimization software helps you to define the right search page, which kind of component and size might make sense. And these components setup then can be set up here in the simulation tool. You have one baseline, and then you can set up different scenarios in addition to this baseline you want to have a closer look to. So in this context here with battery and PVs, that means you can set up different PV sizes, and also you can import the generation of the PV from dedicated simulation software like Helioscope or PVSys or PV Planet, or you can simulate in a simple way by your own in the tool. And on the other hand, you need to find, let's say, different simulation scenarios for battery storage size. So you can take then different C rates, different power ratings, and different capacities. And furthermore, for the optimization of economic things, you also need to define what is a kilowatt hour worth when it's inside of the battery storage, because you need to give the optimization algorithm some kind of benefit that he stores then energy with inside the battery. And when you have set up all these, let's say, parameters, then you can start a simulation that's done step-by-step approach over the simulation period you want to go for. And then we can go to the next slide and have a look on how this simulation then is performed and what are the results of such simulation. So by selecting the different possible simulation scenarios, you can then start simulation by defining, okay, what I want to go for, which period I want to simulate, because really like a step-by-step simulation of this optimizer. And therefore, you need to set up then which kind of dispatch algorithm I want to pick. There are dispatch algorithms that just have a look on the actual data. So they're just looking for the best state, best economic state for the problems they have to solve in energy, which is the cheapest resource of my energy. But there are also algorithms that can have a look in the future. That means with forecasting. So they can have a look, let's, for example, in 15 or 30 minutes, what's happening there, or even in longer time period. And therefore, they're going to make different decision compared to a dispatch algorithm optimizing just looking on real-time data. So therefore, you need to select the right dispatch algorithm within your simulation, but need to take care of that also this dispatch algorithm later on, you need to have the capability that the automation system that later on operates the system also has these capabilities of the simulation you just made here. And if you then later on have then results of generating this time series of this, for example, 20 years simulation period, you can compare each scenario to the baseline. So you have these different scenarios with different battery sizing, different PV sizings, and you can have a look then on the cash flow. You can have a look then on the energy output or the energy imported from the grid or you exported, and also then based on the, let's say LCOE, on the levelized cost of electricity over the entire life cycle. And of course, important fact now is also really carbon footprint you have a look on. And you can export really the simulation results and they give you a good picture to say, okay, I've made my simulation. I found out my best, let's say, scenario with sizing for battery and PV, where I have the best balance between cash flow, best balance between maybe carbon footprint, and so on also, of course, with the levelized cost of electricity. And and since these reports, you can generate different way, like different dashboard outputs you can make there. You can generate heat maps about the energy output in time series for each day in high resolution, let's say, for the simulation with PV and battery behavior. And also then here on the right-hand side, you can see a Sankey diagram. Maybe you can just put next button, then we can see Sankey diagram a little larger. Then you can see, for example, this energy flow with inside of the 1 year, where you say, okay, I have my PV inputs, it's going also as well into electricity, I import power, but I also now, when it comes to buildings, it's more and more important to decarbonize. And this could be a way to say, okay, I'm going to electrolyze my heating system as well. I'm going to use a heat pump, and so off you can also see, okay, I have here interlinked between electricity generation and also then regarding heat generation for my building. And that's very useful outputs that then will be used to define and set up the real system for the project. And that we will see then here on the next slide, how this then in real operation looks like. So so you can see example for a campus. So with a campus, we have various systems that need to be interlinked. It's a quite complex energy infrastructure looking to electricity, thermal, heat, cooling. And therefore, you need, first of all, have a transparency. And this just can be done by collecting all data from the system. So on best case, you have then a building automation system where you get all data then from the building consumers. And on the other hand, it's also important that when you set up some systems that you really can control also your battery system and generation on site in that manner that was used for the simulation before. So if you have some system with a forecasting in the simulation, you also need then some automation systems that has capability for forecasting. And here we could see an example of a campus infrastructure that also takes into account new energy consumers like the EV charging infrastructure. And therefore, there we see you have really a good forecasting. It's important that you get additional information from the EV charging users than might be when they just plug on the car. So for example, here in this case, the e-car user can use the app where you're just going to note down, okay, my current car has this state of charge of battery. I want to have it fully charged and I'm going to leave at 6 in the evening. So that means, okay, the system now knows, okay, this amount of energy is needed to charge this car here within the next hours. And based maybe also on the forecasting I have now for my PV generation, the system is able to predict the PV output and when it comes, and therewith can really make a planning of each charging process for each individual EV car. And therewith you can really optimize the use, for example, of green energy for charging of electric cars. And this is handled over this backend system from the EV charging stations in combination with the Siemens optimizer. It's called here in this case DIOP. This has a capability to include forecasting and well as now is connected to the energy market. So that means has information about tariffs from the exterior. And so can really set up, okay, what's the best way when to charge the car, or let's say how to use my consumers. And also this flexibility of the systems and can be commercialized at the energy market because you have the capability to control every consumer mainly within the building that's connected to the system. And also then we see EV charging. And therefore this flexibility with battery storage in addition then can be commercialized in the terms of a demand response market. Yeah. And then Narayan, maybe then on next slide, I can give you an introduction how this can be monitored and this performance can be monitored. So we have heard before that we're starting with a simulation setup. We call it also kind of simulation already. We're starting with the digital twin because you make a baseline setup. You're going to really say, okay, what consumers are installed, how do they behave? And now in this case where you have installed the system, you can really match each other. So what does the monitoring data, real monitoring data of system match with the digital twin we have there in simulation? And therefore, we have this Mindsphere Application Center, it's called, for distributed energy systems. And here in this example, I've shown you some things we are going to monitor for battery systems in the microgrid especially. So we can monitor really the cell temperature on rack level and also then on system level and make trend analysis if there's some cell might behave on the way it shouldn't, so there maybe it's heating up. And also then the battery container temperature, the SOC estimation, we can make by our own with the system because we've recognized that all the manufacturers have a BMS, battery management system, but this doesn't really tell you the state of charge of the battery in an accurate manner. And therefore, we also have the possibility to estimate state of charges of battery by our own. And also what might be interesting is you can compare the behavior in the battery. What is the state of charge the battery has been stored as in the meantime? So what's the average state of charge? Because, for example, at NMC battery types, there's impact on the battery lifetime. So what is the average SOC you have stored the batteries? Or and also can make state of health calculation of the degradation. We can see here on the right-hand side, there we have a battery system that has been installed 3 years ago, and since years ago is in operation, and we've simulated the degradation based on the user profile and based on the predicted profile. And now we've seen it really matches this degradation, which that we have just, let's say, simulated beforehand, compared to that one that's just mentioned by the battery management system. So it's still at 100%, but in fact it isn't because it's in series, it's in operation. And we could prove this because we also made capacity tests on site with the battery system to really find out what's the actual state of health of the system. Yeah, and this similar things were also done in the past for microgrid simulations, also for example for mobile base towers that should be run completely self-sufficient. And therefore we also have different optimization targets, for example, that foresight generation is minimized and shouldn't exceed, let's say, 1,000 hours operation within a year. And therefore the simulation software and also then the monitoring here can help really to optimize then the system. Narayan can go to the next slide because that really summarize up what I have told you before. So It's really covering the entire project lifecycle from project development phase, where we're going to create a digital twin by our simulation, where we set the baseline, and then we're going to simulate it. And based on the best simulation results, then the real system is set up. And this real system setup then feeds back the real measured data to our digital twin on optimization algorithms. And then they can run in addition and run once again and optimize the system in order to identify additional parameters that can be optimized for the operation of such a system. And now my colleague Nayan is going to show you some project example where we've done exactly this, and also is going to elaborate a little bit more on those digital services we can offer then during the operation of such systems.
Thank you, Sebastian. Thank you very much. Yeah. So like Sebastian said, what we thought is that we will show and demonstrate what we have done for Princeton. So this is again very close to the Princeton campus, and this is within the Siemens facility. So what DOE, for example, the Department of Energy and Princeton, many universities, they wanted us to kind of do a facility, a microgrid facility where they wanted to understand and research on it. So this was done in Princeton. What we had done, so SIMS basically means supply improvement measures. So we distinguish low side items, for example, chiller, pumps, lighting into demand side measures. These are supply side measures. So, and what we had proposed for Princeton was a PV of around 1 megawatt, let's say 836 kilowatt, a battery storage system of 1 megawatt hour. Along with this system, what we had also done is the microgrid control application. Now, just to again put it in perspective, we are doing a very similar setup in IIT Kanpur itself. I hope that you know that there is a pilot which we are doing, a microgrid pilot, and we plan to commission it in a month's time. And it will be great if you could all make a visit and understand that. So most of the systems are also there in IIT Kanpur. The microgrid controller is basically the brain behind the entire solution. So it basically controls and optimizes the performance of the grid, the battery energy storage system, the PV system. Now here in this case in Princeton, we also had to integrate what is known as Desico CC. That is our platform to control low side items. For example, the chillers within the building, providing the air conditioning within a building space, lighting, all those things are basically controlled by Desico CC. Then Mac, see, this is nothing to do with Mac, Apple Mac. We define it as Mac because it's our own cloud service, MindSphere application, which we say for distributed energy systems. So all this data gets collated into the cloud, from which you can analyze it and you in fact can develop your own solutions. We had paralleling of switch gears and futuristic EV chargers. Now these are the latest chargers which are available. VC charge, which are basically vehicle to grid charging. So in case of excess battery power, you can always send it back to the grid. So this is something of the latest development in Siemens. And you would also get a privilege. In fact, we are right now installing it in the campus itself, in IIT campus. And there are two numbers which we are going to install, and those are both vehicle to grid based EV charging systems. So in this case, we had installed 6 numbers. Just an SLD on it, basically you had the grid, okay, then most of it initially was supplied, most of the load was supplied to directly from the grid. What we had done as an addition is to put in solar arrays, approximately 1 kilowatt peak, a battery storage system, all of them connected via transformers, and then we basically connected parallelly to the main utility transformer. So all this, the load which comes from the grid, the solar system, the battery system, all of it, the brain behind is the Siemens microgrid controller. And this microgrid controller, what Siemens has is we have been developing it over the past 15 years. You know, we started this entire business 10 to 15 years back. So there is a lot of knowledge which has been developed and based on which we have developed the microgrid controller. This is a classic example of why we feel, microgrids are a very big solution in the coming future, because Princeton recently, I hope that most of us know that there was a hurricane called as Ida, which had hit the United States. It was a category 4 hurricane. And when it hit Princeton, this particular facility, it was passing through Princeton approximately 2 to 5 p.m. So the advantage here is the system immediately went into island mode when there was, see, we all know that in the United States, you typically don't have power cuts. Okay, it is very low. But in this case, because a hurricane was passing through Princeton, immediately the grid supply basically went out, and there was a seamless transfer which took place. So once the grid supply went out, then the battery started to give the required frequency and the voltage levels to all the PV inverters to continue generating power and supply load to the facility. Those kind of advantages which we have in a microgrid system is huge. And this was in fact a great, it was appreciated in fact by the Princeton University also, because there was seamless transfer. And though the entire area of Princeton had a 4-hour power cut during the hurricane period, there was seamless transfer and there was no power cut within this entire facility. So the battery basically gave the reference voltage and frequency to continue running the PV system, even though there was no power. This graph, in fact, clearly shows during that particular period, you can see the blue, light blue plot is basically the solar power that was available. This is the load of that particular facility. Okay. And initially, before the hurricane hit Princeton, so the grid was supplying. So the grid, in combination with the PV solar, it was supplying most of the load requirement. Suddenly, when the power cut happened from the grid, there was a seamless transfer which took place, by which the battery kind of took over the entire loading requirements. So the grid went out, which is denoted by this light brown line. The grid went out, the battery in combination with the solar started to take care of the entire load. Okay, so from around 215 all the way, and you can also see that the battery, which is indicated by the storage system, which is in white, you can see that there were certain periods when there was excess solar power, the battery was also charged, so the entire load was catered by the solar system, and as well as charging the battery. So this went on till the power came, and then there was complete resynchronization, and we connected back to the grid, and the battery was kind of stopped discharging. So now these are the phenomenal achievements which we didn't even think possible for the power. 5 years back, 10 years back, we wouldn't have thought this was the seamless a transfer of energy can take place. But right now, with the Siemens microgrid solution, we are able to achieve that. And pretty soon you will see it in your own pilot, which you are developing in IIT Kanpur. So Siemens, like I said, over the last 15 years, we have been working in the space of energy and sustainability. Why we are doing this again, the Princeton Island Grid is basically, we also have a energy efficiency program. We have a very ambitious target that Siemens is a huge organization, but we have to go carbon neutral by 2030. That is a target given by the management. So over the last 6 years, from 2.2 million metric tons, we have reduced it all the way to 50. So right now we have a 50% reduction, and in the next 9 years, we have to go carbon neutral. And our main focus in Siemens, we have around most probably 150 to 200 factories, but all these factories, we have energy efficiency programs, both on the supply improvement measures as well as the demand improvement measures. A lot of focus on renewables, fleet emissions, reducing that by putting into EV. In fact, now all the Siemens factories have 2-3 EV parking stations. If you come to any, you're always welcome to come to any Siemens factory and see the kind of advancements we are doing with renewables and fleet emissions. So the main agenda why we did the Princeton Island Grid is basically, it's a partnership in the US, like how we are working along with IIT Kanpur. It's a partnership there with the DOE, which is the Department of Energy, national labs, and all the universities around the place, Princeton University and all. It's a research hub. Again, it's a research hub where we put in all the most innovative projects which we develop. We typically put it there. It's an open demonstration, so whenever clients, or if you are interested, if you're ever in Princeton, you can have a visit of the facility. You're always welcome. And it's a lighthouse project. So Siemens, whenever we do different projects, we classify them as lighthouse projects. So what did we do there? It's basically putting in a 1 megawatt hour of battery, a solar system, okay, a photovoltaic system. Your battery will be connected, your grid is connected, and you have EV chargers, vehicle to grid EV chargers, like I said. All of that, the supply side, when we are talking about supply side, we are focusing on battery. So a battery system, the EV chargers and the voltaic, all of them communicate to the microgrid controller, which goes into the cloud. And when we talk about building, when we're talking about heating, cooling applications, lighting applications, all of that basically gets communicated via Desico. It all goes into cloud where a comprehensive analysis comes out. So this cloud is again getting developed, I mean, month on month. So once it reaches the cloud, all the data which gets collected comes in a seamless report for analysis, basically. So what we are focusing in Princeton, not only Princeton, I'm sure IIT Kanpur also is all about optimization of microgrid and the building performance, Internet of Things, performance monitoring and analytics, which is a big component right now. And we're talking about digital twin. So when we're talking about digital twin, it is basically a what if scenario. So we all know these are equipments and they tend to degrade over a period of time. So digital twin is all about creating what if scenarios. So what if the solar is new, and what is the production available to what it is currently. So that is what is digital twin, and it is picking up in a big way. And we are always secure. So there's no worries on the cyber security part. So this is again a very broad thing. You have solar panels, battery inverters, transfer switches, and then EV charging stations. I wanted to talk about two more very, latest developments which we have in Siemens. One is DESMAC. We call it DESMAC. It's basically a cloud application, MindSphere Application Center for Distributed Energy Systems. And the second is, it might be of interest right now in US. It is picking up for many universities. It's called a SEVA. It's basically an Indian word. It's about Siemens Energy Workplace for Analysts. So these are two things which I thought I should talk about. So DESMAC, when we talk about MindSphere application, so what happens is typically people tend not to analyze. So they put in a solar plant, they put in a battery system, and then they just about leave it at that. That was the trend even in India over the last 2 years. Yes, certainly now people are worried about KPIs, which is the key performance indicators across many of our competitors and many of our clients. But before that, people were not really interested in KPIs. So what DESMAC does, so DESMAC is not only restricted to solar PV, it can do with cogeneration systems, engines, it can do with battery systems. So all the data basically gets captured, okay? For example, inverters give out data, sensors tend to give out data. So all this data gets captured. We use cloud. We have no particular, we don't want to stick to a particular cloud. We can use any type of cloud. In this case, it is AWS. And the output, because the algorithms, we have made analytic based engines and domain specific. Domain specific means we have domains for PV, we have domains for gas engines, we have domains for batteries. All those things come out and we give multiple outputs in terms of visualizations, monthly key performance indicators, performance statuses, as well as REST API. If you want to integrate it to an existing SCADA or an HMI system, we can also push REST APIs. This is a classic example of DESMAC. So, okay, other than the customizable and interactable based report, which we will be giving typically to customers every month right now and to research facilities and universities. Other than that, the kind of advantages, for example, let's just take a scenario here, plant soil losses, okay? What was happening is before DESMAC was not installed, there was no way we could really understand the impact, the commercial impact because of soiling on the PV panels. So after we installed DESMAC, over a period of time, we saw, so basically daily soiling losses again is based on a digital twin philosophy. It's basically to understand what if scenario, what if you actually clean the panels, what can be the generation be, and what are the losses which we are currently facing. So you can see the daily losses kept on increasing all the way. And somewhere in October 10th or something, or 2020, they cleaned the entire panel. And you can see the kind of impact it is happening. You can't get it back to original design because equipments and especially solar components always degrade over a period of time. But you can see the significant drop when it came to the losses. Okay. Similarly, you can the other parameters which we track, for example, long-term degradation. It's very important to understand how much the plant is degrading. Okay, so when you meet any vendors, they will say typically the first 1 year you might have a 2.3% loss. Okay, and after that you would have a gradual loss of around 0.65% every year in terms of performance. Now, is it actually happening? We don't know that. So all those parameters are also tracked. So from here, in this case, from 2019 all the way to 2021, these parameters were tracked, and you can see the degradation actually happening. So that this is the advantage. So we are moving into an era where analysis is becoming critical. It is no longer about just installing a PV system or an engine. It's no longer that. It's all about analysis right now. And all our clients also, we see a shift towards them also understanding the value of analysis. So again, only for if you look at PV, the kind of the package, the asset monitoring value which we provide is the availability, the yield, and these are all 15-minute interval. If you want, we can increase the interval all the way to 5 minutes. You can reduce it to 1 minute. Though people don't ask us, we can have that kind of detailing when we are talking about yield every 15 minutes. What is the yield, the energy performance index, the availability, how much energy is there, performance ratio, which is a critical parameter when it comes to solar. A lot of them commit, okay, we can give you 0.80 as the performance ratio, but is it actually happening in site? Nobody would know that. So we give performance ratios, inverter efficiency. If we all talk about inverters being European standard, but is it actually delivering it? What is the loss across the inverter? All those parameters are defined, and we give that in terms of report. Again, this is just to show you the different dashboards which are available. I have already spoken to you about, this is an actual incident. So these are not, this has actually happened in site. So this loss regarding solar, I have clearly explained it. Regarding the digital twin, which I kept saying about, it is all about what if scenarios. So ideally, what if your solar panels are delivering to the maximum? So when you install a solar plant, when it's clean and new, you can generate around, let's say, 1,300. That is the expectation. So that analysis, the what if analysis, is basically based on experience which we have. Okay, what is actually measured in site? So actually it was measured at around, let's say this, the blue line indication is around 1,000 kilowatt. Now after cleaning, after they correct that particular error, was it an inverter error or was it a cleaning loss, a soiling loss, then the generation has obviously increased. So this kind of analysis can be done on an hourly basis, a what if scenario, what is actually in field, and after you correct that particular incident, whether it's an inverter failure or whether it's a PV soiling loss failure, how much is the new level of energy generation. And again, practical examples. For example, you can see the tracking which is happening here. So these are the different types of losses: the failure loss, the degradation loss, clipping losses because of inverter. There are clipping losses during inverter design, which we take into consideration. In this case, you can see there was a plant failure at somewhere around February 1st. Okay, so in one of the plants in US. Again, what is the impact when it comes to USD? Finally, when we have to meet clients, there is always a commercial aspect to it, right? So when we talk to clients, it's always about how much is the impact when it comes to cash finally. So these kind of things, in fact, what happens is immediate rectification. The client gets a notification on his cell. He sees, okay, 200, there is an issue here. Then they can pinpoint to what is the issue, where is it happening? Is it the inverter? If there are hundreds of inverters, in this case it was 25 inverters, in case if there is an issue with inverter number 25, let us rectify it. So that is the kind of advantage data brings in. And you can in fact see the maintenance team also. The maintenance team gets the notification when a failure happens, they immediately go rectify, and then they completely eliminate this kind of huge losses which typically used to happen 4 to 5 years back. Just a classic example is we had installed a 1.8 megawatt PV plant in California. And So before they installed DeskMac, okay, there were 25 inverters. It showed problems, okay, but people didn't realize what is the kind of impact which it had, for that particular facility. So we installed DeskMac, started to monitor the system. We came to know exactly which inverter was not performing. So in this case, we through heat maps and through graphs, we came to know that inverter 25 was completely malperforming. It was not performing at all. There was approximately a loss in terms of USD around 6,500 USD. And just by rectifying this small issue, we were able to get around 6.6K, 6,600 USD in terms of savings just from one inverter. So imagine when you have hundreds of inverters, soiling loss, the accumulation of losses have a direct impact on the commercial value. So that is why we at Siemens always say analysis is equally important. Installing components is great, but analysis also is a very important part when it comes to microgrid solutions. So again, when we talk about DESMAC, it is not only to do with solar PV. I've just given an example of solar PV, but we all know that microgrids are trending towards a combination. So it's so DESMAC, these kind of analysis softwares are available for battery energy storage system, for your diesel generator sets, hydrogen, combined heat and power systems. And we classify those kind of measures under DESMAC. And Navigator, which basically for again a cloud-based solution which focuses on the demand side. So when we're talking about building lighting systems and building automation, heating systems, all of them get classified under Navigator. So we have a entire spectrum when we do an analysis, yeah, from the supply side to the demand side. So DESMAC is all about, the web platform which is available for basically people to understand, especially for plant managers, operator maintenance people, chief engineers, including your CTOs, the chief technology officers, all of them to understand where they stand at with regards to the plant and what is the KPIs, are they achieving it or not achieving it. But what we also have is Siemens Energy Workspace for Analysts. That is why it's derived. I mean, the short form is SEVA. It's all about, the thing is when we talk about DESMAC, it is all about giving out parameters because we have algorithms which we have developed, algorithm engines, and it gives out parameters. And if you look at it, not many operation and maintenance team, they would like to program and they would like to analyze stuff. Okay, so they would like to get direct data so that they can rectify the issue. But Seva is all about, so it's basically web-based Python environment for developing analytics, visualization, and applications. So it gives an opportunity to all of us to develop. You want to develop, let's say, something on performance ratio, something on performance yield of a solar plant, something on the state of health of a battery system or state of charge of a battery system. So this platform is an open-ended platform where you can program. You don't have to depend upon the cloud software anymore. You can program, and given whatever inputs it is, and then finally you can create your own dashboards. So that is why we feel Seva is a very good tool, especially for institutes like you, research institutes like you, and people who are keen to understand more on energy. Yeah. So when we talk about DESMAC, it is all about for standard users. So for example, a CTO wouldn't want to sit and program. So it's all about standard users to understand the KPIs. They want to just focus on usability and they want to get the target done so that there is no commercial loss which they foresee. So data is beautifully visual. You can see the data in beautiful charts and bar charts. Whereas Seva, what we do is typically target data analysis and scientists. Okay, it's basically you guys have the power to analyze the data. There is so much of data, but the data gets streamlined. So once it enters our system, the data comes out streamlined towards you. So you don't have to really make templates to streamline data. It is already streamlined. It comes to you and use it. Data is available in standard Python, which is very useful for all of us. It's all about you get, so typically if you look at it in terms of DESMAC or the data explorer, you don't get access to the plant data, the raw data and all that. So here you get complete access to that, and that is how you can play. You can adapt new visualizations, new reports. You can create your own widgets. So that is the aspect of Seva. So that is why we called it as a workplace for analysts, basically. So the main focus again right now, Seva, there is a lot of focus, especially in Europe, and it's coming to India. And we'll be more than happy to help if any of the IITs are really interested in Desmark, Seva, or any other microgrid projects. But the main focus is of Seva is obviously for university facilities, for you, for all of you to kind of do your own analysis and develop solutions. And it's basically a living lab. And IIT Kanpur, the microgrid which we are doing is a classic example of a research based project. So Seva can be a very good addition to that. We also give this to multiple O&M providers, and mainly it's and if you have if you are enthusiastic about energy analytics, then these tools are really very useful. Desmax, Seva, and also the simulations what Sebastian showed before my pitch. And finally, see, we kept talking about Princeton, and we showed you a case study on Princeton. But let me say that I feel one of the best projects which we are currently doing is obviously IIT Kanpur, because Princeton, you had a battery system, you had a solar system, you did have all these advanced applications like Seva and Desmac and all those things. But a complete microgrid picture is your own system. So once you commission it, it would be great if you all could visit it and understand. It's a remarkable system where two villages, we took two villages. One was Chaba Nevada and Bhargavdyapur. It was 40 kilometers away from the campus. Okay. And in one of the villages, we had put in a battery system, a solar PV system, and a biogas system. They were not big in quantity, but all the systems were provided, including 6 solar pumps, which we had provided within the facility. Similarly, in the other village, which is 1 kilometer apart, we had a battery system, solar PV system, and solar pumps. Okay, in total, all of this is provided with smart metering system. Basically everything was linked via smart meter. All the data gets communicated to your control center in IIT. Okay, within IIT itself, there were 2 pilots. One was a semi-urban pilot and urban pilot. Okay, again, where there were battery systems, solar PV systems, and also we have installed 2 EV charging stations. And in fact, those 2 EV charging stations will cover, let's say, the most modern portfolio when it comes to EV charging. Because we are also installing a vehicle to grid charging there. 2 numbers are there within the campus. So once it's activated, it'll be good if you guys can use it also. So this is an incredible system, and we really are thankful to IIT to partner with us to develop this particular project. So, but the main contention again here is this particular project. Once we show it to the DST and once UI assist is pleased with it, the idea is again how we can develop it for India. The concept behind the pilot was semi-urban, urban, and rural. So it's very similar to a condition like, let's say, Pune, for example. You have very similar things. In the exteriors of Pune, you see a lot of villages. You see a lot of villas for especially the developing middle class where they stay. You have high-rise buildings. It is again how we integrate all this via microgrid and then supply the required power to all these areas. So that's it from our side. I hope all of you really enjoyed what we could present here, though it was a very short duration, but we are really thankful that you gave us an opportunity. We will present this slide. We will give these slides to Arindam. I think he can share it. The thing is,
Sure.
if you have any inquiry, please call me up, and you can also call Sebastian, and we are more than happy to help you any time of the day. So thank you very much for this opportunity.
Very well. Thank you, Mr. Menon and Mr. Kran, for this wonderful session. So we have a few questions from the audience side. So I would like to present to you.
Yeah.
So one of the questions is that solar generation is fluctuating in nature. Do you find power quality issues such as voltage and frequency variation in the microgrid due to fluctuating nature of solar PV?
Yes. Sebastian, would you like to answer that?
Yeah. So Yeah, I think it's really related, let's say, to the capacities of the grid forming units within this microgrid. So, for example, you have to look on the maximum short circuit capacity of the generating units that can form there, for example, a microgrid. And if you have the right sizing, let's say, of the inverter capability of the battery system and with the power output compared to the PV system, then it can really regulate on a very transient level, on really fast, let's say, regulation. And also, it's just interesting if you have several grid form units with this one microgrid, it's very important that each others are really parameterized to the others, that you don't have any oscillating effects. And that's something we assume is also going to make studies of, for, therefore, especially. And there's some project I can mention. It's made for Hawaii Islands. So Siemens is in really to analyze and make studies for Hawaii Island if there's a pure grid just formed by inverters. So there's no rotating generating equipment anymore there in the future, and you don't have any inertia. And therefore, it's really important also if you have a larger microgrids that this oscillation effects, let's say, related to the inverters, are really managed. So really is that you have, let's say, a management system on the grid level that can really manage this true curves for frequency and voltage, let's say, regulation of each inverter, so that it doesn't come to such oscillation effects.
Okay, that was a very nice explanation. I hope it clarifies the doubt of the participants. And next question which we have is this. As you have mentioned that you are doing the project in Princeton, which is a pioneer research university. So the twin module, which is over there. So in that, can we only fetch historical data from that, or researchers can also test their hypothesis? Like as Sebastian has mentioned that there's certain optimization coding going on between BESS and PV, and there's certain new optimization algorithms in academics also. So can the researchers also test their hypothesis in this digital twin subsystem?
Absolutely. That is where, so in DeskMac, which is the kind of monitoring report which you get, in that you can't. So, but in Seva, which is the tool for and a workplace for analysts, we just open the entire platform for you. So you can in fact make your own hypothesis, create your Python, your system based on it, and then we can compare it. Yeah. So it's an open platform, Seva, or basically research and analysis. So you can test the hypothesis. Yes.
Okay. And one last question, like for the time being, we are dependent on this like big generators we have, which is based on fuels and all those things. And because of that, so many greenhouse emissions gases are there. So in upcoming future, is solar and BSS together is going to completely replace this conventional system which we have today? Means will we become totally dependent on BS and solar?
That's a very interesting. Yeah, Sebastian, please go ahead.
I think it's really economic topic also, because, you know, as more, let's say, degree of self-sufficiency you want to reach, let's say with PV and battery only, for example, as more it costs. And therefore, I think there's already, if you're going to go for a high degree of self-sufficiency, you also have to look at the costs therefore. And for example, when I come back to a small example we have made for a simulation for this mobile phone base stations that should be run completely self-sufficient. You can really dimension maybe the battery is that large and the PV is that large that it can run so, but it's very costly. And therefore we need to find the right mixture. So for example, we said, okay, we need to put a gas engine there as well as a backup. But our intention is to run this gas engine as limited as possible. And therefore, for example, optimization target was to say it should not run over 1,000 hours a year, because they need maintenance and make maintenance for it. And therefore, just once a year, somebody should travel to site. That was optimization criteria. Therefore, but then it's really the case. Okay, what is my optimization criteria? And also when it comes then to economics, I think if you just want to go for battery PV, it would be too costly to be completely self-sufficient. But maybe if it's a large grid, then really where you say, okay, for example, in Europe, we have a large grid with a lot of different locations where maybe the sun is shining somewhere else in Italy, but somewhere maybe the clouds, let's say it's north, let's say of Europe. Then it evaluates more, you know, because there is a need maybe of the backup powers and is limited because you have a larger grid where these fluctuations level each other out. So, but nevertheless, I think there still needs to be some kind of rotating equipment still there.
Okay, so we need something sort of hybrid kind of system. Since for something we're dependent on this, because economical aspect also we have to see. So we have to depend on solar as well as a few part on diesel generators and other things also. Okay. Now, next question I have is, you have considered for university how a microgrid will be effective for industry running 24/7 with PV and battery. I think this only we discuss right now with Sebastian. One
Yeah,
question is there.
exactly. Exactly. But again, industry, yeah, if you look at it, if you are going for a very big industry, we are selling projects. For example, right now we are selling a lot of projects, especially to pharmaceutical industries, which run 24 by 7, and ports, for example. Ports is a very big market. But always there is an inclusion of rotary based systems also, like your DGs. It is not complete elimination as of now, because practically, if you look at it, battery is still a very expensive solution. It is not very cheap in the market, because a 1 megawatt battery, 1 megawatt hour battery costs around 5 crores, in Indian currency. It's very high.
Mm.
So if for example, the demand, if the demand for, let's say, a factory is 10,000 kVA or 10 megawatts, putting a battery system to compensate that kind of thing is very costly. So that is why right now, whenever we target industries, it is all about hybrid systems. We say that, yeah, you have a reduction chance of 30%, 35%, but we don't typically commit 100% self-reliance on, only on renewables. But the one more thing which I also want to add is, there is some trend now where we basically partner with a lot of PPAs. PPAs are basically power purchase authorities. So they have a lot of solar farm, wind farms, where they're also installing batteries, and they supply power. So instead of using directly from thermal sources, okay, we typically use green PPAs, combine it with our in-house microgrid solution within the factory, combine both of them, and then try to develop something like 100% renewable based scheme. That is the latest trend which is happening. So yes, there is a trend towards green, and it is achievable because of the green PPAs which are available within the market.
Yeah, thank you, Mr. Menon. And the last two questions we have. Have you implemented DC microgrid? If so, could you explain the details?
DC microgrid.
Yeah.
DC microgrid, no. AC, yes. Sebastian, anywhere where we implement DC?
I just know really microgrid on DC level we didn't do so far because it was so not economic. Because it's kind of from technology perspective, all the loads are mainly really, let's say, on AC side. You really generate also on AC side in many cases. So we're just slightly touching it when it comes to fast charging on EV charging systems, where it might be on the DC level you want to do so, but not really now up to now on our side for microgrids.
Okay. And one last question we'll take, as we already tight on schedule. So one question is that instead of battery, what is another optimal solution for storage in terms of cost and effectiveness?
That's good. Yeah. So Sebastian, storage. See, again, again, storage is an issue. That is the part where there is a lot of research going on. Okay, storage is not cheap right now. Okay, it is an expensive solution. But let's take an example 10 years down the line, when batteries are going to become cheaper. See, 10 years before, if you look at the cost per watt of a panel. Okay, when the industry was starting in India, the cost per watt of a solar PV panel was around 60 to 70 rupees per watt. Right now, we are talking about 18 rupees per watt. So you can see in just 10 years' time, the development, what has taken place in solar. And that is why now we are going and hitting the markets with a lot of solar plants and wind farms. Right now, the amount of research which is going into battery, because knowing that lithium and cobalt, they are an issue in terms of availability also. There's a lot of technology development which is happening with zinc air based battery solutions, vanadium redox based battery solutions. Although they are, again, they're still not cost effective. Yeah, but let's say 10 to 15 years down the line, we can see certainly an improvement in cost. But when you talk about storage right now, it is still very expensive, because hydrogen is also an alternative for batteries. It is not always that we have to depend on battery. Hydrogen is the cleanest source of fuel available, and it's a great great storage system. But again, the cost, when you look at hydrogen, it's really expensive when compared to battery. Yes,
Yeah,
Sebastian.
I think hydrogen really comes then into place when it comes to long-term storage applications, and when it comes to seasonal storage, then really it makes sense because with the storage capability of hydrogen is quite large. But when it really comes to microgrids, I just can say really that electric battery storage system are the state of the art. There are also possibilities, but I think it's really technologies that not developed so far or not really competitive when it comes to cost.
Yeah, that's true. So I think this concludes today's session. So all the participants, if you have any doubts or any queries, you can anytime contact us, or you can also contact Mr. Roshan Kundan and Narayan Menon.
Sure.
And so it was a very thank you. I want to thank Mr. Sebastian Kern and Mr. Narayan Menon for this today's very, very interesting and informative session. And today we have seen a very wide aspect of where the PV and BS is going, not only from technical aspect, but also from
Exactly.
economical aspects, which need to be taken into account. So both of
Exactly.
things is important. So I think it has widened the ideas regarding the researchers have. So with this, I want to present a token of appreciation to Mr. Sebastian Kern for such a
Thank you.
nice session and for accepting our invitation. And also, I want to thank Mr. Narayan Menon and want to present him the token of appreciation. And
Sure.
we
Thank
hope
you,
that
Arindam.
our institutes as well as Siemens both work together when we place new and new milestones and for the state-of-the-art systems, which would really be helpful economically and technically for the time to come in future.
Absolutely.
So, Mr. Menon
Absolutely.
and Mr. Khan, with your permission, I want to conclude this session. So, thank you all the
Thank
participants
you.
for being here. Okay,
And please,
thank you once
please
again.
connect with us anytime. Please connect with us anytime for any doubts. We are always welcome. I mean, you're
Sure.
always welcome to connect with us anytime you want. Yeah.
Sure.
Okay.
Sure. And I will
Okay.
really
Thanks.
ask everyone to just take advantage of these things because there are so many things going out there which really
Exactly.
affects in so many different ways. And that
Correct.
things we cannot assess through books and other things. So if we contact, as they have so much experience, they can help you a much better way in a practical, more practical sense. Okay. So thank you, Mr. Menon. And thank you, Sebastian Khan. So
Thank you.
hope you have a
Thank
nice
you.
day.
Bye.
Thank you.
Thank you. Same to you. Bye bye. Take
Bye.
care, guys. Take care.
Bye. Have a nice day.